So we start to discuss what machine learning can help us in data science. So when we talk about machine learning, so remember when we say machine learning, we mean that we have already some problem we want to solve, okay, in mind. So that means that usually we talk about, let's say we have a data like this kind, right? So we have a data, let's say between the feature and the label, right? Label can be categorical or can be numerical, right? Okay, so given this kind of data, right, apparently we do have a lot of them, right? Okay, a lot of them. So if we want to build up, the relation from x to y, right? So the x will be a bunch of attribute, right? So when we want to build this kind of relation, then we need the help from machine learning. Okay, so here we start from something very simple and very intuitive. That's decision trees, right? And also just because that you learn the deep learning already, right? Uh, in fact, that in history, you know that the deep learning is kind of coming very late. But before that, before deep learning, we do have a lot of machine learning methods such as Digitry and supervised machines. Okay, so you should keep in mind that between deep learning and the decision trees, there'll be a lot of difference. Okay, so we are going to explore that also in this part of lecture. Okay, so we start to talk about deep learning. So first we give some introduction, and then we discuss how to use deep learning, how to use decision tree, and then discuss how to construct a tree based on the ID3 algorithm. Okay, then of course we will use some of the entropy computation to help us to build a tree. So what is this in tree, right? So basically, as a data scientist, right? So maybe from time to time you are going to report whatever you have, the performance, let's say all kinds of models in your mind, right, to your boss, right? So he may not know deep learning very well, right? So, and also, he doesn't have a lot of time, right? So what kind of model that you can present to your boss, right? So these days, of course, maybe you think about deep learning, right? But deep learning is something that we consider a black box model, right? Okay, so usually when we have a very good result, so we don't know why. Okay, most of the time, right? So relatively, on the other hand, that we talk about decision tree. The decision tree is something that may help us to provide the so-called transparent model, right? The transparent model, uh, so which means that on one side that we have, on one side that we have, okay, we have a transparent model. Okay, transparent model, right? So, and on the other side, we have a black box model, right? Okay, yeah, so meaning that, okay, maybe along this axis, so we have a transparent model to a black spot model, right? But on the other hand, probably, probably for the black box model, we have a high, okay, effectiveness. And the low effectiveness, right? Who knows, right? Okay, so we are kind of in a trade of, let's say, either we want a transparent model with a little bit, for this one is relatively that we can have the low and high effectiveness, right? And we are going to choose either the low effectiveness and the transparent model, or maybe we are going to choose the black box model and with high effectiveness. So of course we are care we care about so what kind of gap, right, between the high and low effectiveness, right? But the transparent uh, date model and black box model will be something that is not that easy to change, right? So we need to make our decision. We need to make our decision. So of course depends on the different situations, that either that maybe we prefer effectiveness, or maybe we prefer transparent model with explainability, right? So these days, probably you heard about, explainable AI, right? So that'll be very important, because from time to time, we know a model, we build a model, right? The model looks like effective, right? In certain domain, but we don't know when we move to another domain, can we still have the similar uh, effectiveness? We don't know, right? So if we talk about a Digitry, it won't be the case, right? Even probably we may not have such a very high effectiveness, right? But maybe we can enjoy the transparent model with explainability. Okay, so I think before we go on to talk about Digitry, maybe you have to keep in mind, right? So for the deep learning, right? For the deep learning, and probably you know that most of the time, if we talk about, for instance, image, right? If we talk about images, so if we talk about image analysis, right? So if we talk about uh, speech recognition, okay, or if we talk about text mining, right? For these three things, right? So that we know the deep learning can help us a lot, right? But we know that there'll be tons of machine learning applications, right, or data science applications, that we don't just focus on data like these three kinds, right? So for those data, usually we may not just always choose deep learning to be our solution, right? So maybe we can find out deep learning, find out Digitry is also helpful, right? So that's something that we have to keep in mind, right? So uh, I don't exactly know what could be the most recent statistics, right? But I it's not a surprise that these days, right, for people working on industry, right? So other than, just like I say, other than the three uh, categories, right, the three types of applications, maybe we can still find out Digit tree will be very useful. Okay, so that's why you still need to keep in mind that from time to time you may think the Digit tree will be, let's say, helping you in certain situation. Okay, so here is the tree, right? Suppose that uh, let's say if we want to find a friend, right? So a friend who is interested in playing tennis, right? So maybe this friend either they'll be in his office, or maybe in the tennis court, right? Depends on the weather, right? So if the weather so here is the tree model to describe, okay, for different kinds of weather, right? So your friend maybe in his office, or maybe in the tennis court, right? So that you know where to find him, right? So suppose the weather will be like sunny, or with high humidity. Maybe it's not wise to play tennis, right? Or if it's sunny but with normal humidity, right? then could be okay to play tennis. So if it's cloudy, maybe play tennis is okay, right? It's not too hot, not too cold, right? On the other hand, if it's rainy, if it's a small rain, maybe we can, you know, with not too windy, we can still play, right? If it's with strong wind, then we don't play. So suppose that's the model to sort out all kinds of situations that either uh, our friend will be play tennis, yes or no, right? Okay, so yeah, so that's the decision tree model. Okay, so as you can see that we will have the internal node, right? Okay, and also we have a branch. We have a different branches, right? Okay, so basically we're going to say, okay, so for each of the internal node means a test. We a test on certain attribute, right? So for given the certain attribute, we have the test. Then we are going to follow in different paths, different branch, right? To go down to one layer down, right? Okay, until that we reach a leaf. The leaf will tell us the result either to be positive or negative if it's for binary classification, right? Some other situation maybe we have multiple class classification. Okay. In fact, here maybe I need to emphasize that the attribute that we have here will be mainly nominal, right? Which means that for the weather, right, either to be sunny, overcast, or rainy, right? Or humidity to be high or low, right? It's not going to be like a numerical value, right? So we talk about the typical decision tree, which we only have nominal attributes, right? So of course, later that we can extend to the case when we can deal with numerical data. Okay. Yep. So yeah, so given some coming data points, right? So suppose the outlook is sunny, right? The temperature is hot, okay? The humidity is high, right? Then the wind is weak, right? And we want to check for this kind of situation, there'll be this person will play tennis, yes or no, right? So we go from the root, right? Following because it's sunny, right? So we follow in uh, this path, right? Then we go down to check one more attribute, humidity, right? The humidity is high, right? Then we find out, okay, for this kind of weather, this person may not play tennis, right? Okay, so that's just to show us how to use a decision tree. Okay, so apparently the tree can be used for all kinds of logical judgment, right? Okay, like if the outlook is sunny and the wind is weak, right? Maybe we can use this kind of tree to represent the concept, the concept that we want to represent, right? Okay, so this is another case, right? So outlook is sunny or wind is weak, right? So maybe we can try this, right? So the outlook is sunny or wind is weak, right? When we have the yes, right? Okay, so we can try this kind of tree. So apparently this kind of tree may not be unique, right? Or this is another case, right? For the XOR, outlook is sunny, XOR wind is weak, right? So you can take a look. So in general for a given tree, right? So we can use disjunctions of conjunctions to describe the tree result, right? I mean the prediction from the tree, right? So for this tree, so we do have 5 different leaves, right? So for each leaves, meaning that there'll be a path going from the root, right? Following this path, right? Going to this leaf, right? So for each leaf of and equivalently for each path, right? So we're going to have, okay, something classified as either to be positive or negative, right? Yes or no, right? So then we just focus on for each yes, right? So which means that there'll be 3 yes right here. Okay. So for each yes, then we are going to for each yes we're going to write down a conjunction, right? Like outlook and sunny equal to outlook is sunny and humidity is normal, right? Then we have this yes, right? The outlook is overcast. We have this yes, right? The outlook is rain and the wind is weak. Then we have this yes. Okay. So apparently you know how to uh, discuss what kind of concept that this tree is talking about, right? On the other hand, we can also say for this tree, right? For this tree, we can use the rules as follows, right? To talk about the tree. So these two are like equivalent, right? So if you can imagine that if we want to use the tree to do classification, right? So maybe using the rule down below will be easy, right? Compared to, let's say, we may need to follow the path given a tree data structure, right? That may take longer time, right? So as you can see that for some, for instance, for in computer networks, right? If they want in a firewall, right? If they want to check either there'll be some malicious traffic, right? Then they need to check a lot of things, right? So usually they try rules like this, right? So there'll be some situation, right? Either the such like something something and something something, or something something and something something, right? So this kind of disjunctions of conjunctions to uh, decide either there'll be on the network, there'll be on the firewall, there will be a malicious traffic, yes or no, right? Okay. So that's same thing here, right? So given the tree, then we can transform that, convert it to be a set of rules, right? So the rules will be easier to use, okay, for computers. Yeah. So when that we are going to consider decision tree, right? So I think one maybe the target function is discrete, right? So in this case, it's a classification problem, right? So that could be a good choice that we can use in tree, right? And maybe we allow some noise, which means that if we check the way that we use the tree, right? Sometimes, we see that some of the attribute may not be needed, right? So in this case, even something wrong here, right? Something wrong here. So we don't care, right? So that means we can allow some noise, right? Okay. Which means at the same time, we can also say some missing values will be possible. I mean, will be okay, right? So we can still use the decision tree to do classification. Okay. So apparently there'll be a bunch of example, right? For instance, I think you will feel no surprise that for people for banks to check that some people is like the credit history, right? So we are going to care a lot about uh, let's say usually we're going to use decision tree to help us, right? I think you will not feel surprised, right? Instead of what? Instead of using for instance deep learning, right? So first of all, given the credit checking, right? This kind of situation that we may not have so many attributes, right? And also at the same time, no matter what kind of model that we can build, right? We still need the financial experts to confirm what we have, right? We can not just like a black box model to help us do the credit checking, right? So that would be kind of weird or maybe dangerous, right? So yeah, so we are going to talk about, we know how to use decision tree already, right? So now we want to find out how to build a tree, okay? So how to build a tree actually is rely on a greedy algorithm. Okay, greedy algorithm. So yeah, so greedy algorithm. Okay, so greedy algorithm means what? Means that each time we just need to let's say based on some criteria. Okay, based on some criteria, so we can find out what could be the best decision, right, for at this moment. Okay, then we can such as the for Digitry, right? If we want to build a tree, then for each moment, maybe we say, okay, we don't know how to build a whole tree, right? Maybe we can just find out what is the root, right? For instance, right? What is the root, right? So maybe, okay, we just need to, okay, decide maybe the root will be outlook, right? Okay, then what else that we don't care, right? That's the next step, right? Then we just need to worry about one choice at a time, right? Then after we make the choice, okay, after we make the decision, right? Like, okay, we already know the root will be outlook, right? Then we go down, okay, maybe some other things that we can check, right? Okay, so we never what? We never go back. We never go back, okay? We never go back means that we will not regret that. Like once we decide, once the outlook as the root will be decided, we don't come back to worry that, oh, maybe the root shouldn't be the outlook like that, right? Okay, so that's greedy algorithm. So each moment we use the criteria to decide what could be the best decision, right? So once the decision is made, right, we go forward. We don't go backward, right? Okay, so we also always go forward means that for the next moment, then we're going to say, oh, what could be the best attribute right here, or what could be the best attribute right here, or what could be the best attribute right here, right? So that would be the greedy algorithm. Okay, so in this case, we're going to find out, okay, what could be the best decision attributes, right, for the next node, right? Once that we decide A will be the best decision attribute, right? Then uh, then we assign the one to be the node, right? Then for each of the value for that attribute, right? Then we create descendants for that value, right? Okay, for instance, for the outlook that we are going to have three values, sunny, uh, overcast, and the raining, right? Okay, so then we'll have three branches, right? Then we sort all the training examples along that values, right? So which means that for all the data points, right, we're going to uh, I mean, actually, I can show you what the data could be like, right? That's the data, right? So which means that we are going to have 14 data, right? Given there'll be 1, 2, and 3, and 4 different attributes, right? So once that suppose the root has been decided, that will be the outlook, right? Then we're going to separate the 14 data points into three groups, right? So sunny, there'll be one group, right? The first group, right? Sunny, okay? The second group will be overcast, overcast, and overcast, right? The third group will be raining, right? And raining, and the raining, right? Okay? So then we will have three branches, right? We'll have three branches, okay? I mean, we have three groups, three subsets according for each of the branches, right? Then we go down following each of the branches, right? Then for each of the small subset, right? Okay, sunny, overcast, and rainy, right? So for that group, right? So if all the training example following within that subset, right? If it with the same target value, okay, that means what? That means all the things has been, correctly classify, right? Correctly classify. Then we stop. Then we stop. Okay. So otherwise we continue. Okay. Uh, okay. So there will be some other situation. For instance, maybe no training examples satisfy this value, right? Then we also stop, right? Because nothing, we don't need to do not we need to do nothing, right? Because there's no further training data to give us more information, right? Okay. So for this number 6 and number 7, right? Maybe we stop, right? Okay. So otherwise we continue to iterate and try to find out, you know, more attributes that can be used for further split, right? Okay. So the next question is, okay, how to decide what could be the best decision attributes, right, for each moment, right, for each moment. Okay, so maybe we can simplify the situation like, okay, suppose we have two attributes, right? So one is A1, so one is A2, right? Okay, so maybe the data will be like this, right? 29 positive, 35 negative, right? Okay, then given A1, right? Then maybe following, suppose it's a binary, right? Then for both A1 and A2, right? Then for one group, right, there'll be 21 plus and 5 negative, A plus and 30 negative. If we try A2, then there'll be something like this, right? So anyway, so we are going to decide either A1 should be used or A2 should be used, right? So our that's up to us, right? We have to make the decision, right? So how to make the decision? Actually, we use entropy, right? We use entropy, okay? So entropy is going to compute uh, so we already explained to you in another lecture, right, in the practice session about what's the definition of entropy, right? So maybe we can write down again right here, yeah, to remind everybody, right? So given a random variable x, right? So that's a random variable, okay? Yeah, so we are going to define the entropy of x is equal to the summation of px log, okay, pis log pix, right, for all the different I, okay, yeah, so which means that uh yeah for which means that uh if the x could be, let's say 1 2 3, right, for instance, maybe x is associated with, you know, one quarter, right? One quarter and one half, right? Then the yeah I forgot a minus sign here, right? Then the entropy is going to be what? One quarter times, you know, log one quarter, right? So here the base is 2, okay? Uh, and also one quarter log, okay? One quarter, right? Okay, log 2 times log one half, right? So, and with minus sign here, right? Okay, then the result will be what? The result will be one quarter times log, uh, yeah, let's just write down one more time, right? Okay, so here will be a minus 2, right? So that will be equal to okay, minus 2, right? Okay, this one the same, right? Okay, yeah, so you know that why we need to put a negative sign in front, right? Just because we are going to have a minus, right? So that will make, we cancel that, right? So there'll be this, all the things together, there'll be 1/2 plus 1/2 plus 1/2, right? Okay, so yeah, I think that'll be like this, right? Okay, yeah. So that's the entropy, right? But for this case, just because we only have what? So we only have two groups, right? Okay. So we are going to compute the entropy. Let's say the now the x, yeah, now the x will be only, let's say 0 or 1, right? So maybe we are going to say that 0 with probability p, right? 1 with probability minus 1 minus p, right? So the entropy is going to be uh, like this, right? Like this, okay? Yeah. So yeah. So then, and then let me just write it. Uh, okay, like this, right? Okay. Yeah. So for the function, yeah, yeah. Actually, for this function, right? So the curve is actually right here. Okay, right here. Yeah. So that means what? That means when p is equal to 1/2, right? So we reach the peak, okay, and the value is equal to, the entropy is equal to 1, okay? And I also told you that in another lecture, right? So when we reach to the, when p is close to 1 or close to 0, right? So actually we will have the value converge to 1, converge to 0, okay? For the entropy will converge to 0, right? Okay, so yeah, so we know that, okay, entropy measures the impurity, right, for of S, right? So which means that if the positive group and negative group will be more or less with similar values, similar numbers, right? Then we're going to have a very high impurity, right? Meaning that the entropy will be very high, right? Like in this picture, this curve, right? Okay, so we are going to use entropy to help us, right? So we're going to compute the entropy uh, to decide that either that will be we close to the subset, right? When we have most of them to be positive, or most of them to be negative, or half-half, right? If it's half-half, then we say the entropy is very high, right? So we can try the case like we just discussed, right? So we're going to compute the entropy right here, okay? And also the entropy right here, right? So you can imagine that if the entropy right here will be very low, right? Okay, then we say, okay, suppose, right, the A1 give us the result, and we check the entropy right here. Okay, if the entropy is very low, then we say A1 is good, right? Otherwise, we say, A2 is good, right? Okay, so we are going to compute the entropy. In fact, that in history, right, so people actually talk about a certain concept called information gain. So uh, that is computing the entropy difference between this one and this one, right? Okay, so the information gain is actually computing the entropy for S, right, and also the entropy in the button, on the button, right? Okay, so actually you know that to compute the entropy difference is is equivalent to just we compute the entropy right here, right? Down to the button, right? So what I'm saying is that we want to compute the entropy to decide which attribute will be better, right? So meaning what? Actually, we want the entropy to be lower layer, right? To be as small as possible. So equivalently, we can say we want the attribute to be associated with the information gain as large as possible, right? Because the information gain is actually computing the entropy difference between this layer and this layer, right? Okay. Yeah. So yeah, then we can do the computation like the following, right? For this part, right, the entropy is, okay, suppose we get the answer already, right? 0.71. And for this one, the entropy, yeah, I think, yeah, the computation is like what? The computation is like, okay, for the, for the, for the 31 plus and the 5 negative, right? So we're going to compute like this, right? Like this, okay? Then the result will be like this, okay? Yep. So that's the computation. And after that, okay, then we also can compute for this one, right? For this one, the result will be 0.74, right? Then we do what? Then we actually compute the difference. Remember, the information gain is computing the difference between the entropy in this layer and also in this layer, right? But down to the bottom for this layer, we actually doing the weighted summation, right, for two parts, right? So for this one, actually we weighted by uh, 26 divided by 64, okay? And here will be 38 divided by 64, okay? Yeah, so we do the weighted summation right here, okay? In the end, we get the result. On the other hand, for this one, also we compute and we get the result. Looks like, this information gain is lower, right? So we're going to choose, okay, A1 to be the best attribute for this case, right? Okay, so then if we come back to the data set that we have, right, for the tennis playing case, right? So we're going to try all kinds of, attributes, right? Then we can say for different attribute like humidity, right, like wind, right? We can try it, right? So in the end, that we actually what we get is we are going to choose the outlook, right? After we choose the outlook for each of the subset, remember that we're going to sort all the things, right? According to that, the value equal to, for instance, for the outlook, we're going to say the value could be sunny and overcast and raining, right? Okay, so we're going to try that, and in the end, okay, so that's the outlook, right? Okay, so we compare for all the things that decide that, okay, the outlook gives us the largest information gain. Means that down to the bottom, right, we are going to find out the entropy in the bottom layer will be the smallest one, right? If we choose outlook, right? I think you can compare then to see that result. Okay, so we're going to try the outlook, okay, for the root, right? For the root node, right? Then after that, we're going to sort all the things, right? Which means for this bunch of 5 data points, right, that belongs to the first group, right? And these 4 belong to the second group, right? And the third group, right? Okay, then we find out for each of the subsets, right, there'll be different distributions, right? So for this one, so we know that it will be perfectly classified, right? So we don't have to try any further split, right? But that's not the case for the first group and the third group, right? So then maybe we need to try to have a more split, right? So later we're going to find out, for the sunny case, right? We're going to try the humidity because that gives us the highest information gain, right? Okay, yeah. So in the end, we get the tree like this, right? So uh, all the training data has been, classified perfectly. Okay, in this case, right? But of course, we have to know that when that we can say the tree will give us the 100% accuracy with or 0% error, right? When that we can say that, right? So I would say if we try to split more and more, right, eventually we are going to get 100% accuracy. Okay, so that's what we say here, right? So hypothesis space is complete. That means what? Hypothesis space is what? Okay, hypothesis space is what? Hypothesis space is, okay, so what is hypothesis space? Okay, you can also call the model space, right? Model space means what? Before we decide to try certain model, right? So actually we decide, okay, there's a space, there's a hypothesis space, right? So within this space, we sort, we search, okay, to find out what could be the best model, right? Okay, yeah. So for the yeah, for instance, if okay, if for the yeah, if we are talking about curve fitting, right? So given three data points, we want to decide, what could be the best model, right? Maybe we think about linear model, right? Okay, given 3 points, not too many points, right? So then the hypothesis space will be what? Will be all the linear model, right? All the linear model. Okay, all the linear model means that could be like y equal to ax plus b, like something like that, right? Okay, so then we have to decide the hypothesis space first, right? Usually it will be the case, right? So after that, then we then know, okay, for instance, if we decide that will be the linear model, then we can say, oh, what kind of linear model will be the best to go through these three uh, data, right? So what could be the best, right? Okay, yeah, which means that if we decide uh, the hypothesis space to be, let's say, covering all the quadratic functions, right? The answer will be different, right? Okay, so we have to decide the hypothesis space first, right? Okay, so the statement says that for Digitry, the hypothesis space is complete means that hypothesis space is always okay. Maybe I should say the following, right? So we may worry about the situation like okay. So here is some how to decide the hypothesis space. How to decide the hypothesis space. So either we make it to be very big, or maybe we make it to be very small, right? Okay. Yeah, so let's say if we try, things to be very big, right? Okay, then maybe it takes a longer time to search to the best model, right? For the small hypothesis, right? Very quickly, then maybe we can get, you know, the best hypothesis, right? Okay, so so which means that deciding what could be the best hypothesis space would be very not so easy, right? But luckily enough, right? So for the decision tree, the hypothesis space is complete means that okay, the true model is always included, right? So maybe the true model is right here, right? Maybe the true model is right here. Okay, so uh, right? So suppose the hypothesis space is very big, right? True model is right here. Maybe if we decide the hypothesis space to be very small, could be the true model is outside of the hypothesis space, then we may worry that situation, right? So that's not the case for what? For Digitry, right? Because the target function is always included in the hypothesis space. What we mean by that is that no matter what data that you have, right? So for a given data, any data, right? Given any data, right? So we can always train a tree, right? So that the tree will give us, the 100% accuracy on this data, right? Okay, we can always do that. Why? Because for for two data points, right? For instance, right? Okay, for the two data points, right? Okay, yeah. So we can always, let's say, for instance, if this one is suppose it's binary, right? This one is yes, this one is no, right? Okay, so we can always find out. Let's say we should always find out that maybe there'll be certain attribute they are not equal, right? They are not equal. Okay, which means that if everything would be, let's say, if everything would be the same, right? So it doesn't make sense, right, to have the label inconsistent to each other, right? So that means there'll be the noise, right? Suppose there's no such noise, right? Then we have to we 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 must be able to find out there will be certain attribute they are not equal, right? So we can continue to use, you know, for this kind of attribute separate, right, between D1 and D2. So which means that we're going to do more splitting based on, for instance, X2, right? We found out they are not the same, right? So apparently that we can separate the D1 and D2, right? Okay, we can continue to do this until we are satisfied. So that means what? That means the decision tree model will always, you know, for the ID3 algorithm, we can always find a tree that can give us 100% accuracy on the on any given data, right? On any given data set, right? If there's no such the error I just described, okay? Yep. So then uh, for this ID3 algorithm, remember that's a greedy algorithm, right? So there's no backtracking, right? So once that we have decided our choice, right? So we cannot regret our choice, right? Okay. So which means that we may run into local minimum, right? The local minimum means that we may, for instance, if we want to increase, let's say, increase the error rate, right? So if we start from here, right? So maybe we end up with this location, or maybe we start from here, we end up with this location, meaning that would be local minimum, right? So maybe how to arrive the global minimum, that will not be so easy, right? So but basically we can only get local minimum, right? So based on the ID3 algorithm, the greedy algorithm, right? Okay. So sometimes we can say it's robust to noisy data because we're going to decide the label, right? Suppose we run into certain sub tree, right? So it's not all the things. It may be, for instance, 99% positive, right? 1% negative, right? Then we are going to say, oh, for this group, right? Then we just say positive, right? Which means that the negative 1% will be considered noise and they'll be ignored, right? Okay, and also ID3 algorithm prefers shorter tree rather than the longer tree in a certain sense, right? Because once that we can have the perfect split, right, then we will just stop, right? Okay, so actually we say that for the ID3 algorithm, we say that the BIOS means that we prefer something rather than another, right? Even that both of them, give us the same uh, accuracy or error rate on the training set, right? Okay, so actually, for the ID3 algorithm, we prefer a shorter tree, right? But actually, it's not always that we can say we can produce something as small as possible, right? So basically, it may not be the case, right? Some other things like use breadth search ID3, maybe that can give us a better, shorter tree, but maybe take a longer time, right? Okay, then we talk about Occam's razor. Occam's razor says that we should prefer shortest hypothesis, right? If that can fit the data well, right? Then we don't try something with longer hypothesis, right? Meaning in this case, we prefer smaller tree rather than large tree, right? Okay. So what is the Occam's razor? And basically we say is that the fewer there'll be not so many short hypotheses rather than long hypotheses, right? So which means that if we want to check all of them with the short hypothesis, it will be easier, right? And also with the short hypothesis, if that can fit the data well, right, it's unlikely to be coincidence, right? Most likely could be that we can achieve, something close to the true answer, right? Okay, so there'll be some other issue, right? Like how to on the other hand, right? So how to decide which one will be the smaller or shorter hypothesis, right? So how are we going to do the measurement, right? So that's another issue, right? So if you learned about minimal distribution length, right, then maybe you can see how to, let's say, find some coding. For instance, in this case, we will need to encode a tree, right? To say maybe you can just simply say the tree size is equal to the number of internal nodes, right? Or maybe the number of edges, right? Who knows, right? To decide what could be the tree size or hypothesis size, right? So in general, maybe you can try some other approach, right? Anyway, so we're not going to talk too much about along this part, right? So basically, Occam's razor says that, okay, we should then uh, create a more complex model unless it's necessary to do so, right? So you know that in this case, we talk about deep learning, it's a very complex model, right? So somehow people no longer care about Occam's razor, right? So who knows, right? Depends on different situation. Maybe we still prefer, a smaller model, right? Okay. So here is the concept about overfitting. I think you probably know it already, right? So we can make the judgment about between, let's say, training data, okay, and also the test data, okay, the test data, right? So maybe we can see the curve, okay, to see how to get more better picture, right? So if we try to build a model based on the training data, right, then we use the model to test on the fresh data, and we are going to see the result could be like this, right? For the training data, if we try, the axis will be the tree size. Maybe we can say the number of nodes, right, on the tree, right? So if we continue to, let's say, meaning that if we continue to go further, right, for the tree, right, go split, okay, more split, right, more split, like that, right, okay. So meaning that we're going to make the tree larger and larger, right, and we know that, okay, in the end we can make all the things to be classified perfectly, right, okay, given any training data without a noise, right. So the thing is, if we try to go along this direction, right? If we try to go along this direction, then it's the situation that we go along the x-axis, right? If we try to make the tree to be larger and larger, right? But we are going to find out that for the training data, right, the accuracies continue to increase, right? But after a certain moment, right, after a certain moment, the test data, the accuracy on the test data will drop, right? So what we mean by that is, okay, so the training data will always go up, right? For the test data, maybe after a certain moment, okay, will go down, right? So here will be the turning point, right? Actually, right? So uh, going to the right, we say that's overfitting, right? Okay, to the left we say underfitting. Okay, underfitting. Yep. So maybe we can choose the tree, size, tree with the tree size close to what? Close to somewhere right here, right? Somewhere right here. Okay. Yeah. So to go further, there'll be not so wisely, right? Okay, because we may run into the overfitting situation. Okay. So we can also try cross validation, right? We mentioned that in okay, so we mentioned that in another video streaming, right? Okay, so we can try to avoid overfitting based on maybe we can think about other than the trying the cross validation, right? So here there'll be one choice, right? But that's not only choice, right? We can also try to avoid overfitting by minimize the two things at the same time, right? We try to minimize the number of errors, right? So we also want to minimize the tree size at the same time. Of course, in between there could be certain alpha. There'll be some kind of balance parameter, right? Such as that maybe there'll be like a number of the tree size, right? Maybe the tree size plus alpha times the number of errors, right? Okay, number of errors. Okay, yeah. So uh, that could be the one way to avoid overfitting. Other than that, we check the cross validation result, right? Okay, so let's take a break right here.